Hello, everyone. Welcome to the March 25th lecture for Calc 2. Reminder to complete your web assign by Friday and submit your notes each day on Moodle. Today, we're going to learn about approximating elementary functions by polynomials. Why do we like polynomials better than other functions? Well, evaluating a polynomial only requires multiplication and addition. If you ever take computer architecture class, you will find out how computers do these operations. However, calculators and computers cannot evaluate things like logarithms or exponentials, or sines and cosines. We can't evaluate them either. So how does your calculator approximate what these function values are? What does it do? The purpose of all of what we've learned about series has been to make you familiar enough to know how this works. So we're going to start off with a very simple approximation that you've seen before in Calc 1. So let's say I have some function f. Okay, here it is. Here's my function f. And here is the point at c. Okay, so this is the point c comma f of c. All right, how do we approximate it by a polynomial f? That is the goal. The goal is to approximate f by a polynomial p, because we know how to add and we know how to multiply numbers, and that's about all we really know how to do. So let's think about a polynomial that has the same value at c as f does. What really basic polynomial do you know that is equal to the function there? And furthermore, let's say we want their derivatives to be equal. Let's say we want the value of p prime of c to equal the derivative f. What polynomial does this? It's equal to the same y value there as f and equal to the same slope. Well, you probably know what this is. This is the tangent line. So the tangent line is the first degree approximation of a function. I'm going to follow the book in this series so that you will have a reference. It's good to hear it two different ways. So let's begin. So let's look at first degree approximations of f equals e to the x. So degree 1 approximations. Okay, so, well, let's pick a value, c equals 0, and let's find the tangent line at that point. Well, we need to know what f of 0 is. F of 0 is e to the 0, which is 1, and f prime of 0 is also e to the 0, which is 1, because we all know that the derivative of e to the x is still e to the x. So I need a line that goes to the point 0, 1 with slope 1. And the line we get is 1 plus 1 times x minus 0. Or in other words, what we get one second. Is 1 plus x. All right. So we're going to call this P1 of x. All right, so let's take a look at the graph so far. We'll take a look at it on Desmos. Okay, so we see that the red curve is our function e to the x, and our blue curve, well, line, is the function 1 plus x. This is a degree 1 approximation of e to the x. And what you'll see, if I annotate it, is that near this point, that's the point 0, 1, my approximation's pretty good. But what about my approximation out here? Any good? No, my approximation up there is pretty bad. And so we want to get a better approximation of my function e to the x. How do we do that? Well, it's probably not a bigger surprise that we should use a higher degree polynomial. And that's exactly what we're going to do. So let me switch back to our whiteboard. So we need to use a higher degree approximation. All right, well, what do we do? Well, first we set we'll call it P2 of 0 equal to f of 0. And we set P2 of 0, which I'll tell you in a second, derivative equals the derivative of our function. How do you think we can get a higher degree polynomial? Well, we should set the second derivative equal to f double prime. So we know that f prime is e to the x, and f double prime of x is e to the x. So all of these values on the right are going to be 1. So we need to find a degree 2 polynomial so that when I plug in 0, I get 1. When I plug 0 into the derivative, I get 1. And when I plug 0 into the second derivative, I get 1. So let's try to solve for that polynomial. I know that P2 of x must be a constant number plus some constant times x plus some constant times x squared. And we're going to solve for these coefficients. So I know that P2 of 0 is 1. And what this tells me is that that's the same as A0. So now I know what A0 is. Now I know that P2 prime of 0 is 1, and P2 prime of x is equal to A1 plus 2A2x. So P2 prime of 0 is equal to A1. So A1 must be 1. Well, you might think you know what the pattern is, but let's see what P2 double prime of 0 is. That's still 1. And P2 double prime of x is 2A2, which tells us that P2 double prime of 0 is 2A2. And then these are equal, which tells us that A2 is 1/2. So after all that work, we found out that P2 of x is 1 plus x squared over 2. That's our degree 2 approximation. And if we look at Desmos, let's write that function down. Let's do 1 plus x squared, plus x plus x squared divided by, oops, almost done. Let's see, divided by 2. Okay, so we actually have to zoom in here quite a bit to see the difference between the green line and the red line. Let's see if I can use a different color. Let's use black. Okay. So the red function is the function I want. That's my exponential function. And the black one is this approximation. So I see that the black function is very close to the red function. It does a lot better job of approximating the red line than the blue line did from before. So our second degree polynomial did a better job of approximating my function. Well, how do you think I do an even better job? You're probably not surprised that I use a degree 3 example. So I'm going to have you figure out what the coefficients of P3 are going to be. So we know this should be a degree 3 polynomial. And I know the following information. I know that P3 of 0 is f of 0, which is 1. P3 prime of 0 is f prime of 0, which is 1. P3 double prime of 0 is f double prime of 0, which is 1. And now I need the third derivatives to also be equal. And that's also equal to 1. So I want you to pause the video and solve for A1, A2, and A3. Okay, now that you've had a chance to solve for it, you probably got the following expression. You probably found out that P3 of x is 1 plus x squared over 2 plus x cubed over 6. So you see that there's a pattern going on with the denominators. What is that pattern? What is the formula for the nth denominator? I want you to think about that. Pause the video. What formula are we getting for the denominator? Now that you've had a chance to think about it, you probably came to the conclusion that it is the factorial. And so instead of just using a degree 1 approximation or a degree 2 approximation or a degree 3 approximation, we can use a degree n approximation. And what we should get is something that looks like this. That is the degree n approximation of e to the x at x equals 0. All right, well, let's see how good of an approximation is it. How good is this approximation? All right, let's find out. So let's make a table, and we're going to have our x values and our values of our different polynomials to see how good a job did we do. Okay, so let's have -1, -0.5, 0.5, and 1. And if we plug these numbers into our linear polynomial, we get these approximations for the values of the exponential function. And then I plug them into P2. All right. What patterns do you notice? These are the approximations in red, and this is the exact in blue. Well, what you probably notice is that all of the polynomials and the function are equal at 0, exactly as we said they would be. They're all equal there. But we're not equal when we plug in other values of x. But what do we see? Well, we see that as we plug in x values that are farther away from the number 0, these are farther away from the actual answer than numbers that we plug in that are closer to 0. So the farther our x values are away from 0, the further off we are. However, the more we raise the degree of the polynomial, we see that P3 of x does a much better job of approximating e to the x than P1 does. And so the moral of the story is the bigger the degree of the polynomial, the better approximation you get. So I repeat for emphasis that we are using polynomials to approximate things like e to the x because we have no other way of calculating e to the x that is more effective. So, well, we're going to generalize this, and what we generalize this to are called Taylor and Maclaurin polynomials. So it's a new section. And we're going to actually do this around any value of c. So now we pick c to be any x value we want, be some fixed x value. Okay. And we're going to define the polynomial Pn of x equal to a0 plus a1 x minus c plus a2 x minus c squared all the way up to an x minus c to the n. Okay. So what we can do is set these, or take some derivatives. So let's take the first derivative. we see that the constant term a0 goes away. We have a1, and then we have some other terms. We have 2a2, and then we have all the way up to n times an. And that's raised to the n minus 1. All right, let's take a second derivative. Give you a sense of what's happening. And you get 2a2 plus all the way up to n times n minus 1 times an times x minus c to the n minus 2. So we can keep taking the derivatives until we get all the way to the nth derivative. And all we're left with is n times n minus 1 times n minus 2 times all the way down to times 2 times 1 times an. All right, so what do we do with these? Well, what we do is we plug in c for x and set this equal to f to the derivative of c. So what we do is we plug in x equals c and set equal to f of c, f prime of c, f nth derivative of c. So if you keep track of what's going on, so let's look at this first expression. Let's look at this first one. I'll underline it. What happens when I plug in c? Well, observe that all the terms are equal to 0. So this will be 0, this will be 0, this will be 0. When I plug in c, I find that Pn of c is equal to a0, and that must be equal to f of c. Okay, let's take the first derivative. What happens when I plug 0 in for this expression, for the first derivative? I see the same kind of phenomenon when I plug in c for x. And I get that this is a1, which we set equal to the first derivative. We'll do one more before I show you the pattern. Let's plug in c again here. What do I know is happening? Everything is going to cancel out except for that constant term at the beginning. So this is equal to, when I take the second derivative of my polynomial and plug in c, it's equal to 2 times a2, which is the second derivative. And if I keep this pattern up, what I find happening is that the nth derivative, when I plug in c, will be n factorial times a to the n Okay, so I solve for these constants, and I find that, well, a0 is f of c, a1 is f prime of c, f of c, a2 is 1 over 2 factorial f double prime of c, and this is 1 over n factorial f nth derivative of c. So what you've just figured out are, you have figured out exactly what the coefficients of your Taylor series polynomial are going to be. So we're going to summarize everything we just did and give us the definition of an nth degree Taylor polynomial. So what this has told us just now, Pn of x is our polynomial approximation for f, and it equals the following. And we call this the nth Taylor polynomial of f at C. Okay. And there's a special one for C equals 0. And we call this the nth Maclaurin polynomial. Okay, so the Maclaurin polynomials are just a special case of the Taylor polynomials because Maclaurin did his work separately from Taylor. So I'm going to do an example, and then you're going to do an example. So well, we want to find the fifth Taylor polynomial of sine of x when c equals 0. So this is actually a Maclaurin polynomial. Okay, so I need to find the first 5 derivatives of my function. So f of x is sine of x. That's easy. The derivative is the cosine. The second derivative is the negative sine. The third derivative is the negative cosine. And the fourth derivative is the sine. And the fifth derivative is the cosine. Okay, so what this tells us is that f of 0 is 0, f prime of 0 is 1, f double prime of 0 is 0, f triple prime of 0 is -1, f fourth derivative of 0 is 0, and f fifth degree of 0 is 1. So what this tells us is that our Taylor polynomial, which we're going to call P5 of x, is 0 plus 1 times x. So this is over 0 factorial. This is over 1 factorial. This is 0 over 2 factorial times x squared minus 1 over 3 factorial x cubed plus 0 over 4 factorial x the fourth plus 1 over 5 factorial x the fifth. So if I simplify this, I get x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x the fifth. And so that is the fifth Taylor polynomial of sine of x when c is 0. Okay, now it's going to be your turn. So now it's your turn to find the second Taylor polynomial of f of x equals the square root of x at c equals 4. So go ahead and pause the video and show your work and calculate this Taylor polynomial. All right, now you've had a chance to do that. I will give you the answer, but I expect to see your work in your notes. You should get a Taylor polynomial that looks something like this. All right. So that concludes what we have for today. Tomorrow, we will talk more about how good of an estimate is a Taylor polynomial. Take care.